Good evening, students. Welcome to the week 5 live session of Bioreactor Design and Analysis course. We'll start solving some sample problems. So the first question is, microbial strain is cultured in a 100-liter stirred fermenter for secondary metabolic production. The specific rate of oxygen uptake is zero point 0.4 R inverse, and the oxygen solubility C star L is given as 8 mg per liter. Determine the volumetric mass transfer coefficient, which is KLA, of oxygen required to achieve a maximum cell concentration of 12 gram per liter. So I hope you have gone through the lecture videos for week 5. So let's start solving the problem. We'll first note down the given values. So the volume of the reactor is 100 liter. So C star is given as 8 mg per liter. And the specific rate of oxygen uptake QO2 is given as 0.4 hour inverse, and the maximum cell concentration is X max. It's given as 12 gram per liter. And we are asked to find out KLA. KLA is what? So how do we start solving the problem? Any idea? So it can be given as at a steady state. We can write a relation between what we have already got from the question, which is specific rate of oxygen uptake into your biomass is equal to KLA C star AL minus CL bar. So in this question, for the bioreactor operating conditions, the maximum rate of oxygen transfer occurs when the concentration difference, or when the driving force, which is the C star AL minus AL bar, is highest. That we can make it out as. This can be true when CAL bar was given as 0. So if we substitute this here, we can form a relation QO2 into X max is equal to KLA into C star AL. Can convert this 8 mg per liter into gram per liter, which can be written as 8 into 10 to the power minus gram per liter. So this is again just a substitution. KLA is QO2 into X max divided by C star AL. So now let's substitute what is known from the question. We know the answer for C star AL, which is 8 into 10 to the power minus 3 gram per liter. QO2, which is the specific oxygen uptake rate, is 0.4. And X max given as 12 gram per liter. Let's substitute it here in the equation. The 0.4 hour inverse into 12 gram per liter divided by 8 into 10 to the power minus 3 gram per liter. So what would be the answer? The answer is 0.6 hour inverse. So if we convert it into second, what would be the answer? 0.6 divided by can find that KLa can be found as 0.6 hour inverse. You, so if you want, you can convert it into seconds. Read the question carefully. If it is asked to convert it into seconds, you can convert it into seconds. Shall we go to the next question? So the question is, a scientist while performing a fermentation experiment observed that the properties of the culture medium changed in the process. It now could not flow freely until a threshold stress is applied, after which the shear strain increases linearly with the shear stress. Such behavior is observed in which of the following fluids? Your options are A. Pseudoplastic fluid, B. Dilatant fluid, C. Newtonian fluid, D. Bingham plastic fluid. So, what would be the answer for this question? So, what would be the answer? How we can describe the Newtonian and non-Newtonian liquid? So, do you remember this diagram? CS stress, shape of shearing strain. The Newtonian will grow like this. So, from this diagram, what you can make out? Read the question carefully. The the liquid could now flow freely until the threshold stress is applied, after which the shear strain increases linearly with the shear stress. Any idea? The answer for this question is Bingham plastic. Why it is not a Newtonian fluid? Because it is told that the properties, say for example, due to the stress given, the property is changing, the viscosity is changing. But in case of Newtonian fluid, it doesn't change, where the viscosity is observed to be constant due to the application of stress or force. So we can neglect the Newtonian fluid. So the preferable answer would be being plastic fluid. Next question. Determine the correctness or otherwise of the following assertion and reason. Assertion A is, in agitated bioreactors, the retention time of gas in the broth is minimized. The reason for the assertion is given as one of the major functions of the agitator is to drive the gas bubbles to the bottom of the bioreactor. So the options given are both A and R are true, and R is the correct reason for A. Both A and R are true, but R is not the correct reason for A. A is true, but R is false. And the next is A is false, but R is true. The option E is both A and R are false. What would be the answer for this question? The assertion is, in agitated bioreactors, the retention time of gas in the broth is minimized. That means the amount of time the gas bubbles spend inside the broth is less in case of agitated reactors. The reason is stated as The agitator's function is to drive the gas bubbles to the bottom of the reactor. So, what do you think would be the best option? The answer for this question is A is false, but R is true. Which of the following correlation is true for given flow regime and impeller design? A. For laminar flow, the power number is inversely proportional to the Reynolds number. B. For laminar flow, power number is constant for a given type of impeller. C. For turbulent flow, power number is directly proportional to Reynolds number. D. For turbulent flow, power number is constant for a given type of impeller. So, which of the following statement is true with respect to the flow regime and impeller design? More than one options can be made true. So here the right answer would be for laminar flow, the power number is inversely proportional to the Reynolds number. And for turbulent flow, power number is constant for a given type of impeller. So the question 5 is, some types of fluids exhibit time-dependent properties. The following figure demonstrates how the apparent viscosity varies with time for fluids A and B. Choose the correct option that follows the behavior shown in the figure given below. So you have been given a figure and the options are A represents dilatant and B represents pseudoplastic. And option B is A represents pseudoplastic and B is dilatant. C is Newtonian, B is non-Newtonian. A is non-Newtonian and B is Newtonian. E is thixotropic and B represents rheopectic. And option F is rheopectic and B is thixotropic. So from the figure given, what is the what do you see? Like what does the A and B represents? So from the figure, we can find that it expresses a time-dependent behavior. The answer for this question is rheopectic and thixotropic. where in case of thixotropic, the viscosity decreases actually. In case of rheopectic, increases with respect to time. So definitely not a Newtonian and non-Newtonian. And we discussed in the previous slide the dilated and pseudoplastic how it will appear. So here in this question the answer is rheopectic and B is thixotropic. The question 6 is bulk oxygen concentration in the culture broth in a bioreactor is determined by the rate of oxygen consumption by the cells. The given statement is true or false. This is indeed it's also determined by the rate of oxygen consumption by the cells. So the answer is true. For an immobilized particle, if the Damolar number NDA is less than 1, the mass transfer rate is much greater than the reaction rate, and the overall reaction is controlled by the enzyme reaction. Is this statement true or false? So, why the Damolar number is used? Hmm, this answer is actually true. So let's solve a problem. So here we have a problem about the dynamic method. The dynamic method is used to measure the KLa in a fermenter operated at 30 degrees Celsius, and the data for dissolved oxygen concentration as a function of time during the reoxygenation step is as follows. You have been given the values for time and the air saturation percentage, that is the KL value, the concentration of A in the bulk liquid. So determine the value of KLa in terms of second inverse. The unit should be second inverse. If the equilibrium concentration of oxygen in the broth is 7.9 into 10 power 3 minus 3 kilogram per meter cube. So how do we proceed with the problem? Let's start deriving and then start solving the problem. So in case of dynamic method, that is also during the reoxygenation step only we are calculating. The rate of oxygen transfer will be KLa C star AL minus AL minus your oxygen uptake rate. This is your oxygen transfer rate minus OUR, which is oxygen uptake rate. So in case of dynamic method, we will start, we can take carry out this experiment in smaller vessels. Uh, and this is the most simplest method, and also the other one is static. The another method is there, that is sulfate oxidation method. But here, um, as we are focusing on dynamic method, how it is done. First, we'll sparge air in, and then we will start sparge, like we will strip off the media of oxygen by either supplying nitrogen or stopping abruptly the airflow. And then we will start um, supplying the air in at a constant flow rate. So how the graph would look? So it would be, this is time. So you will supply the air and switch it off. So it will drop. Once it drops not below the C critical value, then you will switch on the air on. From there, you will let it leave until saturation. At two different points, or the number of points, you can use oxygen electrodes to measure the concentration of dissolved oxygen. With this in relation, we can calculate the KLA. So when the DO concentration reaches a steady state value of CAL bar, it means that the concentration of A in bulk is equivalent to the steady state value, because it has reached a steady state. So we can write dCAL by dt is equal to 0, because there is no change in CAL with time. So now the equation which we have written previously, this one, as it is applied 0, it becomes ALA C star CL minus AL minus CO2 into X, and KLA C star AL minus AL equal to of oxygen into X. So here we have to include this condition. So now if we apply, let's keep it as equation 2. So now you know the value of QO2X. This you can apply in this equation. Now the equation becomes L minus equal to, sorry, So now if we simplify, the equation will become KLA. These terms will get cancelled, right? So it will become KLA delta minus KLA KL. You can write it as VQ is equal to KLA KAL minus KL. So now if we integrate it, then we'll get the expression ln of KL. This is the concentration of A at time point T1. This is the time 2. At the end it is T2 minus T1. So now we have found the expression. So now we have to plot a graph between by substituting the values given in your table. The table you can take T1 as 10 and your T2 values can be taken as 15, 20, 30 likewise. So same goes to CAL1 and CAL2 can be varied. So if you start doing that, and also from the table given, you can see the saturation value CAL bar is given as 73.5. Keeping this into account, you can plot a graph between this value, which is ln of CAL bar minus CAL1 divided by CAL1 bar minus CAL2 divided by T2 minus T1 versus time, that is T2 minus T1. If we do that, the graph will appear like this. You can try solving it during the call. So once we get the value of ln and T2 minus T1 is calculated, we can plot it in a graph, get a straight line, and the slope value will give us the value of KLA. So I'll give few more minutes. I'll show the question so that you can copy it down. So for example, here the first T2 is 10 only. So it becomes 0. And then the T2 becomes 15. So 15 minus 10. So that's why the 15 minus 10 is equal to 5 here. This value remains constant, the T1, because that is the time when we start. So here it is 20. So 20 minus 10, so 10. So in case of this, we'll do for the second term. CAL value is 53.5. So this is how the values are taken. So once we uh, solve for each time point and the saturation value, you can fill up the table and then form a graph. From the slope of the graph, we can calculate the KLA value. I hope this clears. So the next question is, an 18 meter cube fermenter is used for the production of biocellulose from bacterial strain of uh, Peigerentia indica. Under the current operating conditions, KLA is 0.25 second inverse, and the oxygen solubility in the broth is approximately 8 into 10 to the power minus 3 kg per meter cube. The specific rate of oxygen uptake is 10.5 millimole gram per hour. Determine the maximum possible cell concentration in terms of gram per meter cube. So let's note down the given values. So what are the given values? Volume is given as 18 meter cube. KLA is given as 0.25 second inverse. Oxygen solubility, that is C star AL, is given as 8 into 10 to the power minus 3 kg per meter cube. The specific rate of oxygen uptake, this Q of O2, is given as 10.5 millimole gram per. So as we solved in the previous problem, the first problem, at steady state, we know that QO2 into X is equal to KLA C star AL minus AL bar. Why? Because for the given bioreactor operating conditions, The maximum rate of oxygen transfer occurs when the concentration driving force, which is the C star Al minus C Al bar, is highest. That is, this can be highest when Cl bar becomes 0. Then it can be kept highest. So this condition will support the maximum concentration of biomass, which can be given as QO2 into X max is equal to KLA into Cl star, because you have applied C bar Al is equal to 0. So to calculate the X max, rearrange it. Equal to this, I have converted into some kg per meter cube. Check the units. So this we are going to convert it into gram per meter cube. So we have to write the conversions 1 by 3600 seconds to convert it into seconds from hour, and to convert the gram moles or millimoles to gram, what we have to do, multiply millimole and also write a conversion for. We do this, what would be the answer? The unit will come as gram per meter cube. That is what we have been asked. Take a few minutes to calculate the answer. I will also calculate along with you guys. So it's 0.25. It's just the conversion. So the answer would be coming around 2.14 into 10 to the power 4 gram per meter cube of X max, the maximum biomass concentration. Okay. So let's go to the next question. A 20 liter stirred fermenter contains a Bacillus thuringiensis culture, and it is used for the production of microbial insecticide, and the KLA is determined using the dynamic method. The airflow is shut off or for a few minutes, and the dissolved oxygen level drops. The air supply is then reconnected, and when steady state is established, the dissolved oxygen tension is 78% of air saturation. The following results are obtained. The oxygen tension is given as for at time 5 it is 50, that is the air saturation. At time 15 seconds it is 66. We have been asked to estimate KLA, and instead of the steady state level is taken as 78%, it is taken as 70%. And what would be the percentage error when calculating the KLA? This is asked. Let's start solving the problem. So how do we start? As it is a dynamic method, we just solved a dynamic method problem. So I hope you can solve it easily. So it is given that the steady state air saturation is 78% and the time point 1 is 5 seconds and time point 2 is 20 seconds. So CAL1 is 50% and CAL2 is 66%. This is from the table given here. So we know the formula in case of dynamic method. What was it? Ln of CAL bar minus CAL1 divided by CAL bar minus CAL2 by T2 minus T1. So we can substitute it. Ln of 78 minus 50 divided by 78 minus 66 divided by 20 minus 5. What would be the answer? So the answer would be around 0.056 second inverse. So the second part of the question has been asked that if in case the CAL value is taken as 70% instead of 78, what would be the percentage error? So simple thing, instead of substituting for 78, substitute it as 70. 70 minus 50, 70 minus 66, by 20 minus 5. Now what would be the answer? So the answer would come around 0.10729. How much is the difference? 10729 minus 0.056, 100% of it, coming around 47.81%. So if there is an error of 8% or 8 while measuring, if there is an error of just the value was around, instead of 78 it is taken as 70, then it would account for about 47.81, almost half. So let's start doing this. We'll start filling how the table was filled. We have filled already two values in the table. 0 0 we filled it. Then we have filled this also, 0.41 and 5. Here again we will solve how this was filled. Fill in the table. Sorry. So it stores all this. Mhm. 0.79 or 0.8 you can keep. So blue. Approximately 3 we can keep. So these are the values. Let's fill it here. 1.6, 2.3, 3, 4.1. This is how I got the tables here. So now you plot it in Excel. You can start plotting now also. So if this is plotted in the y-axis and T2 minus T1 in the x-axis, when you draw a straight line, the slope turning point will give you the KL. I hope this is clear. So why we are calculating the KL value not separately as KL and A? Any idea why it is being calculated as KL and A separately, as A means interfacial area? What does the interfacial area denote? So it is actually difficult to estimate the interfacial area. So when we pass the air in through a liquid or the broth, the interfacial area will be depending on the size and the number of bubbles being present, which in turn is represented by many factors depending on the type of impeller, the impeller speed at which it's circulating the bubbles, or the medium composition and the flow rate. So, and the KL is also affected by various parameters. It is often it is often combined together, and the combined term is referred as the mass transfer coefficient. So, what is the unit of KL? KLA, the unit is S second inverse or time inverse. What would be the unit of KL? So the unit of KL would be the KL is the liquid phase mass transfer coefficient, and the unit would be meter per second. And in case of A, it is the interfacial area, uh, generally described as the gas liquid interfacial area per unit volume of the fluid or the broth which we are using. So this can be written in terms of meter square per meter cube. And when you use the term KLA, can be given as, so this gets cancelled out. So the unit is second inverse or time inverse. Is there any other doubts? Let's wait for a few more minutes. I'll keep looking. So we are talking about oxygen uptake, uh, how the oxygen is getting transferred, everything. So I hope you have come across um, this concept where the steps for transfer of oxygen is explained. So far, we have solved some problems on how the oxygen is getting transferred from the bubble to the media, that is from gas phase to the liquid phase. So how it is now getting into the cells. Uh, we will just have a schematic diagram and I'll just explain the steps involved. So, say for example, let's take it as a gas bubble. And there is a liquid film around the bubble. So let's assume this is a cell, and say for example, so the gas or oxygen has to transfer from the interior of the bubble to the interface, which is the gas liquid interface. This is the step one. From the from the gas liquid interface, it should move across the gas liquid interface, across it, and then move through the. So, for example, it should move from here, the transfer from the interior of the bubble to the interface first, and then it should move across the interface, and then it should diffuse through the stagnant liquid film, and then the fourth step is going into the bulk. This is the bulk volume of liquid, let's assume. So, once it has reached the bulk liquid, this is the bulk liquid, then in case of cells, it is solid, right? So, this is solid cell. So this we can call it as um, liquid and solid interface. The liquid is the broth and solid is the cell. Okay. And the surrounding is the liquid film as we have seen here. There is a liquid film. So now the oxygen from the bulk liquid have to diffuse through the stagnant liquid film, then pass through the gas liquid interface, cross it first, and then pass through the interface and reach the cell. This is true if in case of single cell is there. So, say for example, if the cells are formed as aggregates, example in case of plant cells, where plant cells tend to aggregate in form aggregates in nature. So, if that is the case, or even the mammalian cells and bacterial cells, if they are in clumps or sticking together, so there would be an additional step where through same thing, which is that they have to cross through the liquid interface and diffuse through the stagnant film, and then the oxygen should diffuse through the solid available to the individual cell, and from there it should transport through the cytoplasm to the site of the reaction. Okay, so this is how the transfer of oxygen from the gas bubble to the cell is envisioned. So, as we have discussed about the gas liquid interfaces, I just wanted to discuss about how the gas is or gas here is oxygen is getting transferred from the air bubble into the cell through the bulk liquid. So, any idea on what is oxygen uptake rate? We know the oxygen transfer rate, the rate at which the oxygen is getting transferred from the gas phase to the liquid, and what is the oxygen uptake rate? The definition itself is the name actually. The rate at which the oxygen is getting uptaken by the microbial or the cell system which we are using. So what happens if here we saw there is a critical point, a C critical point. And I told when explaining the problem that below this, your oxygen, you should start the air on and you should not let it go beyond the C critical. What does it mean? Why we are switching it on before C critical level and why it is named as C critical? So the it is a critical oxygen level because beyond which if you go beyond or lower than the C critical level, the oxygen uh, it becomes dependent. The rate of oxygen uptake becomes dependent on the dissolved oxygen. So it should be always. It is important that the oxygen concentration should be maintained above the critical level, C critical, so that the rate of oxygen uptake by the cells remain independent of the dissolved oxygen concentrations. Also, it should be noted that your oxygen transfer rate should not be lesser than the oxygen uptake rate. Then what will happen if you are transferring less oxygen and your uptake rate is more? What will happen if OTR is less and OUR is more? Sorry. The cells will soon undergo into um, starvation mode because your transfer, like oxygen you're supplying, is less and your uptake rate is more. So, what if your oxygen transfer rate is more and uptake rate is less? Your body is constantly supplying air, but the cells are not able to take it up. That will also be will be a problem when you are trying to uh, run the reactor. So we should make sure the critical value of oxygen should be maintained and it should never go below it. I think that that makes us come to a end of the week 5 discussion. If you have any doubts, you can ask me here. Mm. This the example would be plastic. What the example is dilated. So I hope this week's problems we were able to solve. And if you have any doubts, please ping me to the mentioned utilization. Uh, that's all. If you have any doubts, you can ask in the chat box. If there is no doubts, then end this. If you don't have any doubts, you can leave the meeting.